Hi everyone. In this video, just gonna briefly talk about this new notation that we just learned and what it means. Okay. So the way what we've learned is if that's the symbol that's called the integral of a function f of x dx evaluated from the point A to B, right? This basically what it means is it's the area under the curve f of x or y equals f of x between x equals a and x equals b. Okay, so this says if I have a curve and I have a point x equals a and I have a point x equals b, then this basically represents this entire area. However, based on our previous definition, right, of antiderivative, I also know that this shaded, the yellow area, can be found as this large red area minus this other smaller area, which means that to evaluate this is basically you find the antiderivative and you kind of put this vertical line a to b, and you can say this is capital F of b minus capital F of a. Okay, so this symbol is sort of an equivalent of d over dx in the sense that it says that what you're doing is you're trying to find the area of the curve from a to b, and that is equivalent to finding the antiderivative and then subtracting them at the endpoints. So let's look at some examples. 0 to 3 of x minus 1 dx. Now, for this, my small f is x minus 1, so my capital F, so I can find the derivatives, or antiderivatives, which is going to be x squared over 2 minus x, and my limits are 0 to 3. So this would be 3 squared over 2 minus 3 minus 0, which is 9 over 2 minus 3, which is 3 halves, or 1.5. Now sometimes you may be given something that is not directly integrable, or you cannot evaluate it. For example, square root of 1 minus x squared. Now this is not something that we know the derivative of, antiderivative of, right? So what we do is we try to interpret this as an area. So we try to think of it as what area does this correspond to, and we try to see if that gives us something meaningful. So basically we are looking at this function y equals square root of 1 minus x squared, and if you play around with this function a little bit, this is basically x squared plus y squared equals 1, but just the positive half, right? So it's the part of the circle in quadrant 1. So if you plot this integral represents this area. But there's another way in which, and this is 0, 1, we know how to find this area. This area is 1/4 of the area of the circle, so it's pi r squared. So this is just pi over 4. Therefore, you can say that 0 to 1, the integral of 1 minus x squared dx is pi over 4. So since they mean the same thing, sometimes it will be easy to find one of them, and sometimes it will be easier to find the other. And for example, with integrals right now, the number of different functions for which you can find integrals are quite less, which means that you may have to resort to other techniques, one of which in this case is looking at the shape and seeing if it's a recognizable easy shape like a circle, or in this case a quarter of a circle. Now, because of these area interpretations, there are some properties that these integrals have. Okay, one of the properties says that a to b of f of x dx is the negative of b to a of f of x dx. So meaning if you switch the endpoints, it becomes negative. This kind of makes sense because what you're saying here is evaluating the area going from here to here, and then if you invert the process, then that's going to be a negative area. Why? Is because if you think about capital F, it's a cumulative, it's always increasing, right? So if you do f of a minus f of b minus f of a is going to be the same number, just switched around with a negative. Okay. Similarly, if a equals b, then this integral is going to be 0. Which also makes sense because you're saying, what is the area of this line? Okay, and area of a line is always 0. So it doesn't make sense to ask that question. Some other useful properties is if you have a number multiplied with a function, then you can pull that number out and just find the area of the remaining part. If you have the addition of two functions, you can separate them out and you can say it's the area of the first function plus the area of the second function. If you have subtraction in the same way, then you can split them out as saying it's going to be the subtraction of the first minus the second. However, caution here that it doesn't work for products and for quotients. Okay, so we have sort of seen this before, where when we are finding antiderivatives, we did point out that there is no quotient rule or product rule, so it doesn't work like that. And then the last one, which also follows from sort of saying that it's about areas, is a to b f of x dx plus b to c f of x dx equals a to c f of x dx. So what this is saying is, if I take this function, the area from a to b, right, that's a to b fx dx, and then I add the area from b to c, I get the whole area, which makes sense. If there's no overlap and these numbers agree, the lower and the upper bounds, then you can combine them, because essentially you are combining the areas and you get the area of the larger figure. Then lastly, there are three what I call comparison properties of integrals. Okay, so it says if f of x is larger than 0 and a is less than x is less than equal to, then a to p f of x dx is always positive. So let's see, what is this saying? This is saying that if I take this function and it's always positive, right, and I find this area between a and b, then this is going to be positive as well, because it's always above the x-axis. So it's obvious. Second one says, if a function f is larger than another function g in an interval a to b, then integral of that function is also going to be larger than integral of the other function. So what is that saying pictorially? Is saying there's this function f which is always either above g or equal to g, and I consider 2 points, a and b, right? Then basically what this is saying is that the yellow area is larger than the pink area. And so this yellow area is larger than the pink area, which again is you can verify from the figure because you have all this extra stuff right here. Maybe I should mark that in pink, in yellow, sorry. So all of this extra stuff here makes the yellow area larger. And then the last one, it says that if there is some number m, right, and capital M, that the function is always between. So kind of like a squeeze theorem scenario. Then in an interval, the integral of f of x is less than capital M times b minus a and more than small m times b minus a. So what is this saying? This is saying if I take a function here, f of x, between the points a and b, right, and there is some value, right here, capital M, that's capital M, that it is always less than, and there is some value, small m, that is always greater than, then what is true? What is true is that this yellow area will always be larger than this cyan area. What is this area? This area is simply the area of the rectangle. So it's height, which is m, times width, which is b minus a. But the yellow area will also be smaller than the red area. And what is the red area? That's capital M times b minus a. So in some sense, it tells us that even if you cannot find the antiderivative, you can find a range between which those areas are going to lie. For example, if you want to estimate 1 to 4 root x dx, right? So this is root x is increasing function. How do we know that? You can take the derivative, and the derivative is always positive, which means that root x, this is always going to be greater than 1 and less than 2 for x in this range. So the integral is always going to be less than 2 times 4 minus 1 and always going to be greater than or equal to 1 times 4 minus 1. So this is always going to be between 3 and 6. And we can verify. Why or how? Is because we know how to find the antiderivative of x to the 1/2, right? That's x to the 3/2 over 3/2, and then 1 and 4. So this is 2/3 of 4 to the 3/2 minus 1 to the 3/2. 2/3 of square root of 4 is 2, and 2 cubed is 8, and 8 minus 1 is 7. So this is 14 over 3, which is approximately 4.66. So it does lie in that range. And that's a pretty wide range, right? 3 and 6. And you can see from the figure that this inequality doesn't give you a tight range. It gives you a pretty wide range because you have this really small rectangle and you have a very big rectangle. So it's not a great inequality, but it's one that is very simple to visualize and simple to reason that it should be correct. So that's about it for integrals and what we call definite integrals and properties of integrals. The only thing that is left to be discussed is what is called the fundamental theorem of calculus, which is basically, you know, it's kind of formalizing this idea that we have already seen, which is that inverse, that derivatives and integrals or antiderivatives are inverses of each other. So we're just going to formalize that statement and also formalize this particular statement. Okay, and this is a part of a fundamental theorem of calculus. But because of the way we develop this material for as cumulative areas, or we sort of were able to draw this conclusion already. That's it for topics for this week. So the worksheet has some questions on estimation and some evaluations which you can do and interpreting it as areas. And all of these things are now due on December 5. So this week and next week, all combined work will be due on December 5. Thank you.